In this video, we will look at resistor networks. We will derive expressions for resistors connected in series, resistors connected in parallel, and we'll look at a few questions involving both types of combinations. So let's begin by looking at resistors connected in series. Now let's say we have three resistors of resistance R1, R2, and R3 connected in series as shown. Right? So these resistors are connected in series. And of course, let the current flowing through the resistors be I. Now, this is R1, this is R2, this is R3. Now, let the PD across R1 be V1, the PD across R2 be V2, and the PD across R3 be V3. And of course, let the total PD across all three be V. Right? Now, from our look at components connected in series, we know a few things. We know that one, the current flowing through each component is the same. So because these three resistors, R1, R2, and R3 are connected in parallel, it therefore means that the same current I flows through each. Right? Now also what we do know is that because they're connected in series, then the total PD across them, so that is V, is equal to the sum of the individual PDs across each. So say that basically, since they are connected in series, the total PD across them, V, is equal to the sum of the individual PDs across each. Right? So therefore this means that V is equal to V1 plus V2 plus V3. So what exactly does this mean? If in the lab you basically take three resistors and you connect them in series, and you say you hook up a battery so that there's a potential difference across them and there's a current flowing through each. If you have four ideal voltmeters, you connect one voltmeter across one resistor, connect another voltmeter across the second resistor, and you connect a third voltmeter across the third. You take the fourth voltmeter and you connect across the entire combination of resistors. When you take the readings from these voltmeters, the reading on the fourth voltmeter connected across the three resistors should be equal to the sum of the readings on the other three voltmeters. Right? So in theory, they should be identical. But of course, you know that due to, say, resistance of the connecting wires, which in most cases assume negligible, but may be significant enough to affect the readings might not be identical, but they should be very close, right? So V equals V1 plus V2 plus V3. So we say that the total PD across this combination of resistors is equal to the sum of the individual PDs across each, right? So V equals V1 plus V2 plus V3. But of course, we know that from Ohm's law, V is equal to IR. So based on Ohm's law, we have the equation V is equal to IR, right? And of course, we let RT be equal to the total effective resistance of the combination. Right? So what this basically means is that in the case of the total PD, V, we can say that V is equal to IRT. So I is a current flowing through each resistor because they're connected in series, And RT will be the total effective resistance of the combination, and the aim is to basically get an expression for RT, right? So V is equal to IRT, but of course V1 is equal to IR1, V2 is equal to IR2, and of course V3 is equal to IR3. And since of course V is equal to V1 plus V2 plus V3, it follows that IRT is equal to IR1 plus IR2 plus IR3. Since I is common, well, to both sides, of course, we could factor out I on the right hand side, and then i's will cancel. So we'll have basically I RT is equal to I bracket R1 plus R2 plus R3. The i's cancel, and what we're left with is that RT is equal to R1 plus R2 plus R3. So what does it show us? This basically shows us that if we have three resistors, each of resistance R1, R2, R3 connected in series, then their total effective resistance RT is equal to the sum of the individual resistances, right? And this not only applies to three resistors in series, but to any number of resistors connected in series, right? So generally, if we want to increase the resistance in a particular circuit and we have a few resistors, then we typically connect them in series, because their resistance will add to give us the total effective resistance, right? Now, having looked at resistors in series, we'll now look at resistors connected in parallel. So this time we will still use three resistors, R1, R2, R3, but of course this time they will be connected in parallel. So we have R1, R2, R3, right? And these are connected a junction right there, junction. We have a current I which is flowing into this junction. So let's call this, of course, R1, R2, R3. Right? Now the current I is flowing into this junction. Now when we looked at resistors in series, we said that the current flowing through each resistor was the same, because in that type of combination or connection, the current sees only one path to flow, and because there is a connection in that path, the entire current basically flows in that path. In this particular case, when the current gets to this junction, it sees three paths, 1, 2, 3. So therefore the current splits, and a portion of the current will flow along each path to each resistor. So let's call the portion flowing up here I1, flowing to resistor R1. This is I2, and this is I3, right? But of course, I1 flows through R1, I2 flows through R2, I3 flows through R3, and of course they will recombine at this junction, and the total current I, of course, will flow from this junction, right? So we spoke about the individual currents, or the individual branch currents. Now let's talk about the potential differences. Now, because they're connected in parallel, it therefore means that basically the potential difference across this entire combination is the same, right? So if we take a voltmeter and we connect the voltmeter across the combination, then we'll get the same potential difference, right? In this particular case, if we were to look at the currents, if we connect 4 ammeters, 1 ammeter here, 1 here, 1 here, 1 here. The ammeter connected here will give a reading which is approximately equal to the sum of the readings on the ammeters placed here, here, and there. So in this case, basically, the total current flowing into the junction must be equal to the sum of the individual branch currents, right? So the total current I must be equal to the sum of the individual branch currents. And therefore we say that the total current I, so total current is equal to the sum of the individual branch currents, right? And so we can say that I is equal to I1 plus I2 plus I3. All right? So the total current I is equal to the sum of the individual branch currents, I1 plus I2 plus I3. But of course, we must recall that according to Ohm's law, V is equal to IR, right? So V is equal to IR. Now, because V is equal to IR, then what we will do is to make I the subject of the equation, right? Which therefore tells us that I is equal to V over R, right? Now, once again, what we will do is we let RT be equal to the total effective resistance. Now, having said that, it would therefore mean that the current I is equal to V over RT. I1 is equal to V over R1. I2 is equal to V over R2. And I3 is equal to V over R3. And since, of course, I is equal to I1 plus I2 plus I3, it therefore follows that V over RT is equal to V over R1 plus V over R2 plus V over R3. And since V is common to both sides, we can factorize and then cancel or divide through by the V's, right? So we get V 1 over RT is equal to V 1 over R1 plus 1 over R2 plus 1 over R3. The V's will cancel, and so what we're left with is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And this expression, or this equation rather, gives us an equation, or gives us a way of calculating the total effective resistance of 3 resistors connected in parallel, right? So this equation was derived for 3 resistors connected in parallel, but of course it can extend to 4, 5, 6, or even a larger number of resistors connected in parallel, right? So usually if we want to find the total effective resistance RT, we'll find 1 over RT by working out the right hand side, and then of course we'll reciprocate that value to give the total effective resistance RT. Now, having derived the expression for the total effective resistance of 3 resistors R1, R2, R3 connected in, say, parallel, we will then look at what happens if the resistors have identical resistances. What if we have identical resistors connected in parallel? We'll see how this expression changes or can be simplified. So, suppose R1 equals R2 equals R3, and let that be equal to R, right? Then what we have is this: 1 over RT is equal to 1 over R plus 1 over R plus 1 over R. So basically what we have on the right hand side is well, 3 fractions with the same denominator, and so we can just add the numerators. And so we have 1 over RT is equal to 3 over R. And if you simply flip both sides, then what we get from this is that RT is equal to R over 3. What this basically shows is that if we have 3 resistors, each of resistance R connected in parallel, then the total effective resistance RT is equal to the resistance of 1 divided by 3. So basically this means that the total effective resistance in the circuit will be a third of the resistance of each resistor, right? Now generally, if N identical resistors each of resistance R are connected in parallel, then the total effective resistance RT is equal to R divided by N. So therefore the total effective resistance is equal to the resistance of one of the resistors divided by the number of them. So for instance, if we have 10 resistors, each of resistance say 1,000 ohms, then what we have is RT is equal to 1,000 ohms divided by 10, which will give us 100 ohms, right? So basically what we've done is to derive the expression for the total effective resistance of 3 resistors R1, R2, R3 connected in parallel, and we've basically shown how that expression changes if these resistors are identical. And what we basically show is that if you have n resistors, each of resistance R, n identical resistors, each of resistance R connected in parallel, the total effective resistance RT is equal to the value of one resistance or one resistor divided by the number of resistors, right? So unlike series combination of resistors where the total resistance will be larger than each individual resistance, when it comes to parallel connection of resistors, the total effective resistance is always smaller than even the smallest of the resistors connected in parallel, right? So effectively, connecting resistors in parallel is essentially a way of getting a smaller resistance without actually having to go and find a single resistor of that particular value.